Today we're going to talk through Systems of Inequalities, section 6.5. A couple reminders about graphing inequalities. Your inequalities, remember, are when we do not have an equal to sign in our equation, but rather we have something like y is greater than 3x plus 1, or y is less than or equal to 3x plus 1, where we have an inequality there. Couple major differences. The first one is you could have a dashed line. So dashed lines are when we're going to have just a greater than or less than symbol. Or we can have a solid line, and that's when we're going to include the equal to, so less than or equal to, greater than or equal to. And that's one of the big differences. It can be a dashed or a solid line. Second big difference is it's no longer that our graph is just a line, but it's going to be an entire region. So our graph, we're going to shade one side of our equation. So we're going to shade a region. So if I'm going to graph this one here, this y is greater than 3x plus 1, I'm going to graph it with a boundary line as if it was the equation y equals 3x plus 1. This is my boundary line. And I want to graph that, but I want to keep in mind that it's going to be a dashed line, this one is, because that inequality is a strict greater than inequality. But it is my boundary line here. So I'm going to start at my y-intercept like I would any other line, and then I go up 3 over 1, up 3 over 1, and I get my points. And this is going to be a dashed line because I'm not including my equals to. It's a strict greater than symbol. I'm going to clean up that right a little bit so it's a little bit more dashed for us. And what I need to do now is I need to figure out which side, which region I want to shade. Do I want to shade the above region or the region that's below? And there's a couple ways you can do this. You can look at your equation and say, well, it's a greater than symbol. So I want my y to be bigger, so I'm going to shade above it. Or you can pick a test point. So I can look at this point 0, 0, and I can say, okay, if I were to test the point 0, 0, I would plug in 0 for x and 0 for y, and I would get this equation here, this inequality. 0 is greater than 3 times 0 plus 1, where 0 is greater than 1. But that is a false statement. So because it is a false statement, I do not want to shade the side with 0, 0, but rather I want to shade the side above the line, the one that does not include 0, 0, because it gave me a false statement. So I get that this entire region here is what I want to shade, and that is my graph for my inequality. The entire half of that coordinate plane above that boundary line. So we're going to do a bunch of examples right here. We're going to graph some inequalities. So we're going to graph these two inequalities here, and what I want to do is I want to figure out where they have a shared graph. Where do their graphs overlap? And so now my inner overlap isn't going to be just a single point, but rather, just like the individual graphs, it's going to be a whole region. So I'm going to look at this first one, y is greater than or equal to x, and what I want to do is I want to graph the boundary line. So my boundary line is going to be y equals x. And then I want to remember if it's going to be dashed or solid. And this one here is going to be solid because we're including that right there. So it's going to be a boundary line. It's going to be a solid line. And my solid line boundary line is this y equals x. So that's going to be this line here. And now I need to decide if I'm going to shade above or below. And again, there's a couple ways we can do it. One way is to just look at that inequality and say y is greater than. So I want my y values to be larger, so it's the above. Or I can pick a test point. Now this one I cannot pick the point 0, 0 because that is on my boundary line. You always need to pick a point off that line. So I could pick the point, 0, 5, or 5, 0, or -10, -5, but I can't pick anything on my line there. So if I did a boundary or a test point here, I could test the point 0, 5. And if I do, then I get 5 is greater than or equal to 0, which is true. So I want to graph the side that has that point. So 0, 5 is right here. So I would want to graph the side of my equation, my side of my line that has that. So it would be this entire side is shaded in. So that's my first inequality there. My second inequality, if I do that one in green, some beautiful Christmas colors here, is this y is less than 6. So my boundary line is going to be y equals 6, but this time I do want it to be a dashed line. I want it to be a dashed line because that is a strict inequality. So the red one was a solid line because it had the equals to. But my boundary line here for y is less than 6 is going to be a strict inequality. So y is less than 6 or y equals 6, that is a horizontal line that goes through the point 0, 6. So that's going to be this boundary line here. Straight horizontal line. And now this one is probably easier just to look at it. Do I want the y values that are above 6 or the y values that are below 6? And since y is less than 6, I want the ones that are below. So for this one, when I go to graph this, it's going to be this entire region down here. And so when I'm looking at a system of inequalities, I am no longer looking for just one point of intersection. We do have that. Our one point of intersection is this point here. But I'm not looking for that when I do my system of inequalities anymore. System of inequalities, I am looking for where the two regions overlap. So that would be this area right here. So now I don't have just a single point as my solution, but I have this entire section of my graph. That is my system solution. Very colorful. It can get a little tricky when you're doing it all in just one pencil. If you have multiple colors, you can do that. Another way to avoid this, or to avoid all the confusion potentially, is to do the arrows that you see there. I did it with the green one. You could have done it as well with the red. Instead of coloring all of this in, we could have just done some arrows to figure out which side of that red line I want. To show you what I mean in a second. I'm trying to save myself from redrawing that green line, but it may not be worth it. Yeah, we'll just do it all. If I look here, I've got that green line in there, which I'm going to fix in there. I'm going to finish drawing that in again. Here's my green line, and I want below the green line. So I want this area, everything below the green line. But for that red line, I wanted everything above it. So I could draw arrows in for the red line as well. And then you can see just from looking at the arrows where we overlap, and that our overlap is in this section here. So you can save yourself a little bit of coloring in if you need to. Make things a little bit neater if you don't have different colors, if you're just using pencil, to keep yourself from going a little crazy with where all your other sections are, the various sections are. This one here, we don't really have a system anymore. We just have one single inequality, but it does involve both x's and y's. And so if you recall that this is our boundary, if I replace the inequality with an equation, is now the equation of a circle. So we do need to remember how to graph circles. So my boundary is here, and this is going to be a solid line because of the equal sign underneath that less than symbol. But this is going to be a solid line. And so when I graph my circle, I do need to remember how to graph a circle. So I've got my center point at 3 comma negative 4, because remember it's always x minus the x coordinate, quantity squared, plus y minus the y coordinate, quantity squared, and y minus negative 4 gives me that positive form, is equal to my radius squared. So my radius squared is 9, so my radius has to be 3. So starting from that center point, 1, 2, 3, 1, 2, 3, 4, I get my center point, and then I can build out from there. And so I want to go 3 in each direction, left, right, up, down, 1, 2, 3, and I can draw in. I do want this to be a solid line. So there's my boundary, but now I need to figure out, am I going to shade on the inside of that circle, or am I going to shade on the outside of that circle? And you can try to reason through it with your inequality there. The inequality is the less than symbol, so you can think about how we want to be within the circle there. But I would pick a test point, and a test point will always work for us. So nice, easy test point can be anything not on my boundary line. I'm going to pick 0, 0. All right, if I were to put 0, 0 into this equation, 0 minus 3 parentheses squared plus 0 plus 4 parentheses squared is greater than or equal, put the parentheses in there correctly, greater than or less than, that's going to change the question there, less than or equal to 9. I want to know if that is true or not. If that is a true statement, then I'm going to shade with 0, 0. I'm going to shade the side of my equation that has 0, 0. If that is a false statement, I'm going to shade the side that does not have 0, 0. So 0 minus 3, negative 3. Negative 3 squared is 9. So I get 9 plus 0 plus 4 is 4. 4 squared is 16. And I want to know, is this less than or equal to 9? And you can quickly see that it is not. It is a false statement. So I do not shade the side with 0, 0. So if I look at the two sides of my circle here, I have the inside and I have the outside. 0, 0 is on the outside. So if I want to shade the side that does not have 0, 0, I want to shade on the inside. So I would shade inside my circle, and it's every single point in there, including the boundary because of the equal to sign. The less than or equal to. So here we don't have the inequality, we don't have a system, we don't have two equations, we do just have the one. This system has 3 equations. And so again, just like before, we're going to do them all individually. And then I want to list off what the vertices for the solutions are. So boundary line for that first equation is our parabola. Boundary line is our parabola. Y equals x squared. But it's going to be a dashed line now, because it has the strict inequality. So we're going to plot some points. I've got 0, 0. There's a bunch of ways you can go about graphing these parabolas. I like to build out from my vertex. So 0, 0, 1 to the right, 1 up, 1 to the left, 1 up. So 1, 1, negative 1, 1. 2 goes up to 4. 1, 2, 3, 4. Negative 2, positive 4. And then negative 3, 9. Got a stray point in there. Negative 3, 9. And I want to draw in my dashed parabola here. And again, I wanted to figure out if I'm going to graph above, shade above that, or shade below that. A couple ways. You can do your test point, or I can say I want all the y's that are bigger than my parabola. So that's going to be all the y's in here, and I'm just going to do my arrows for the first time so I don't have all the different shading going on, but I want all of that. I want that entire region. My next one here is I'm going to look at this circle. Oh, excuse me, not a circle. I'm misremembering what problems I've got here. I should just look at what I see. This is a line here. And so what I'm going to do is I'm going to rewrite this. I'm just going to subtract the x over and make this y is less than or equal to negative x plus 6. So here my boundary is going to be a solid line, y equals negative x plus 6. And it is solid. It is not dashed because we are including the equal to sign. So I'm going to start up at positive 6. And I have a negative 1 slope. So I go down 1 to the right 1. Here's one part of my line, and I continue on in the other direction here. And I need to figure out if I'm going to shade above or below. And I can look at that y, that inequality here. My y is less than. So I want all the ones that are below, below, below. And now I can move on to my last one, which is also a line, but this time it is just a vertical line. So when it's just the x variable, it is a vertical line. My boundary line here is x equals negative 3, but this time it is going to be a dashed line. So 1, 2, 3. At negative 3, we're going to bring in a dashed line here. And I need to figure out if I'm going to shade instead of below, above or below, to the right or to the left. And since we want the x's that are larger, that's going to shade to the right. So there's a lot going on here, but you can hopefully start to see where all three of these overlap. They are all going to overlap right in the middle. So inside the parabola, but underneath that red line. Let's see if I can get this to color nicely for me. There we go. That's decent sized, I guess. I can make that a little smaller. That's pretty nice. So you can start to see where these overlap, and you can pick out where we have these vertices. So I've got one here where all three of the equations intersect, where just the parabola and that first line intersect. And then down at the bottom, we have one more vertice at the vertex of that parabola. So what we can do is we can go through and we can list off all of our vertices. And some of these are going to be a little easier to list off than others. So that one at the bottom, the vertex of the parabola, that one's pretty easy. That's at 0, 0. So one of my vertices, 0, 0. So if I label that as A is at 0, 0. My other one, this one B here, where the first line, the red line, and that parabola intersect, so that x plus y less than or equal to 6, it's y greater than x squared. Those two intersect, and I can use the graph to help, but I do want to verify that the point I pick off my graph actually does work for both equations. So my thought is that this equation, or excuse me, this point B is at the point 2, 4, but I do want to quick check that. And this is on our boundary line, so we're going to check the y equals and say, does 4 equal x, 2 squared? And since it does, it works for the boundary line on the parabola. And then a check really fast, is 2 plus 4 equal to 6? And it does. So that's a quick little check. That is one of my vertices. So 2, 4 is a vertex. Last one is this point where all three intersect. Again, I want to make sure, I know my alphabet, this is a C, that all 3 points, all 3 lines do intersect at that same point. But I can use the graph to help me. If it's going to go through that purple line, that last line there, x is going to have to equal -3. And then I can do a quick little, I think it's going to be at 9, but we'll just double check. So we're going to say, is 9 equal to -3 squared? It is. Is -3 plus 9 equal to 6? It is. And is x equal to -3? It is. So since it works for all three, and that's where the three equations are intersecting, that's where my vertex is, then my vertex C is at -3, 9. And tomorrow, the next section, in section 6, I think it is, we're gonna look at how we can use these vertices to help solve some systems of inequalities, some word problems that we have. We're gonna set up one right now, and we're just gonna find our area that we're looking at. But tomorrow, when I said we're going to use those vertices, we're going to be able to maximize or minimize a particular situation we're looking at. So here we have our concert event. There are $30 for reserve seat tickets, $20 for general admission tickets. 2,000 reserve seat tickets are available, and fire regulations limit the total number of paid customers to 3,000. The promoter must take in at least $75,000 in ticket sales. And so we want to find and graph a system of inequalities. We'll use our graphing calculator to help us graph these a little bit. But we do want to first identify what our variables are going to be. So I'm going to have x equal the number of reserved seats and I'm going to have y equal the number of general admission seats. Tickets. All right. I know that reserved seats cost $30 and general admissions cost $20. So I do know that I've set up one of my inequalities. I'm going to have 30x plus 20y. Now this is going to give me the amount of money that I want, or the amount of money that I take in. And so if we look a little bit lower, the promoter must take in at least $75,000. So the amount of money we're taking in, it's going to be shown by that 30x plus 20y. And I need that to be at least $75,000. Well, at least means greater than or equal to. It is the lowest it can go. It can equal it, but that is the lowest it can go. I want it to be larger, but it can be equal to 75,000. So this is one of my inequalities right here. My other inequalities, or my equations, because you can have equations in here with our inequalities, but we have that there are 2,000 reserved tickets available, which means that x cannot be larger than 2,000. I can sell all 2,000 of them, but I cannot sell more than 2,000. I can sell less, but I can't sell more. And then my last one says that the total number of tickets that we sell, my x plus y, has to be less than or equal to 3,000, because you can't have more than 3,000 people in the arena. So these are my three equations, my three inequalities that I have here, and I do want to graph them. So I can look at my graph here. I can try and graph them. Now, there are some unidentified restrictions, like you're not going to sell negative tickets. So your x and your y are always going to be at least 0. So I can focus on just the first quadrant over here. And that x is less than or equal to 2,000. That's going to give me one of my boundary lines, which is going to be a vertical line when x is equal to 2,000. And I want to shade to the to the left of that, because I want to be less than that line. I want x's to be less than that. But then I can go through and I can practice my graphing for all of these. So I'm going to work backwards. I'm going to graph this last equation first. I'm going to rewrite that as y is less than or equal to negative x plus 3,000. And this is where you can use your graphing calculator to help you. You can rearrange it. Now, your graphing calculator has to take equations only, but you can get the boundary line drawn in. And I know if I start up at 3,000 and I have a -1 slope I'm going to hit down at 3,000. But here's my equation. Where's my boundary line? I do want it to be a solid line. And I'm going to shade below. You can already start to see where our overlap's going to happen. And then that last equation that we have up at the top there, and I do want to rearrange that. I do want to solve that for x. This equation here, if I rearrange it a little bit, I'm going to have to erase some of this a little bit for us, is I'm going to get not such a pretty equation, but nothing terrible. I'd get negative 30x plus the 75,000. So y is greater than or equal to negative 3/2 x plus 3750. I think we should probably double check that. Mental math divided by, yep, 3,750. So that's going to start a little bit higher, but it's going to come down at a -2, slightly steeper slope than the light purple line. And we're going to get some, we're going to try that again. Nice straight line here. Something like that. Trying to think of where it would hit on the x-axis. Let's try this really fast. If I plug in 0 for y, 75 divided by 30, 2,500. Okay, it's gonna hit. Oh, we're gonna try that one more time. 3rd time's the charm. There. So you can start to see, and I'm gonna graph. I want to be above that line. So you can see there's just one tiny sliver right in here where we want to be. So there's not a lot of area where they want to be, where they can be making that $75,000 or more. But there is that possibility. So later we're going to talk about our vertices here and say, okay, if this is my little region that I need to be in, one of these vertices is actually going to maximize some other equation, some sort of limiting or constraining equation. But that's what we're going to talk about tomorrow. So right now we're just looking at what that region is. So you can use your graphing calculator to help you. You do have to adjust that window. Remember, we do want to have a maximum x value of 2,000, so that's an easy max to put on there. You could do the min of 1,000, or you could do the min of 0. Either way is fine, but you do need to adjust your scale. So you can see here, this blue line is that y is greater than or equal to negative 3/2 x plus the 3,750. And then that red line down below, that one is the y is less than or equal to negative x plus 3,000. So you can see I want to be below the red line, but I want to be above that blue line. And so I do just have this little sliver right in here. There's not a lot of space, and we have that other constraining line here of the x's. So there isn't a lot of area in there, but that is the little region that I do want. So we're going to continue to practice this tomorrow, and we're going to introduce with more word problems how we can find a max or min to some constraining equation.